let's continue our discussion of Kerr nonlinearity based optical parametric oscillators, right? So last time we discussed, so the setup is something like you have some ring cavity, right? And you could have some coupling waveguide, and then you send a strong pump wave, let's say at some frequency omega p, and then once it, so if you send this at one of the resonances of the cavity, then it enters the cavity and circulates in the cavity, and the intensity builds up by a factor of the finesse, right? And so if this medium has a third order nonlinearity, you can, and if the phase matching is also satisfied, then you can get this four-way mixing process to happen, right, within the cavity. And this process will give rise to gain for this signal and idler frequencies. And if that gain overcomes the losses in the cavity, then you can get bright light out at the signal and idler frequencies. Right, and so last time basically we were discussing sort of the properties of the optical resonator, right? How does the resonance look? How does it line width depend on factors? How do the resonance spacing depend on dispersion, etc. Right? So basically, what we saw was that so to phase match this four-way mixing process, right? To phase match the four-way mixing, we need this delta beta total to be close to 0, right? And we've seen previously that that means we need anomalous dispersion. So the GVD beta 2 in this waveguide or the fiber which is making up this cavity has to be less than 0. And then last time we saw if we have a cavity which has beta 2 less than 0, then if you look at the resonances in such a cavity, basically the spacings, so this is frequency, then the resonances are not equally spaced. Right? Only if beta 2 is equal to 0, then the resonances are equally spaced. If beta 2 is less than 0, then turns out that the resonance spacing or the FSR increases with frequency. Right? Of course, each of these has a particular line width. We saw it given by the Q factor or the finesse. But yeah, so the problem is. So again, this is beta 2 less than 0. So what we do is we pump at one of the resonance frequencies, right? And then we want to, so energy conservation implies that, right? So 2 omega p is omega s plus omega I. So that means omega s and omega I have to be equally spaced about the pump. So if you choose any resonances about the pump, so you can go one resonance away on either side or two resonances or whatever, but if they are not equally spaced, you can see that if you choose this as omega s and this as omega I, then omega s plus omega I is not exactly equal to 2 omega p because these spacings are not exactly equal. So right, so then the question arises, how do we get the process to happen, right? So recall that we derived these or the spacings for these resonances taking into account just the linear properties of the cavity, right? So we just took some propagation constant and the dispersion beta 1 and beta 2, right? And we took some round trip phase equal to multiple of 2 pi, right? And that phase we took was just the linear phase, right? So e to the I beta z, and we said beta z. So when for z equal to 1 round trip, so the round trip length is L, then beta L is equal to 2m pi is the resonance condition, right? But we know that if you have if the medium has chi3 or which means it has a nonlinear refractive index, then there are also nonlinear phase shifts, right? So if we want to consider the phase shift acquired in a round trip, then ideally we also have to include the nonlinear phase shift, right? So if we look at the round trip phase, we can write it as the sum of the linear and the nonlinear phase, right? So the linear phase is the one we considered in the last class. So for the mth, so let's say this is the mth resonance frequency, so m minus 1, m minus 2, m plus 1. So then this is beta at the mth resonance frequency times the length, round trip length of the cavity, right? So this was the phase we considered last time. But there's a nonlinear phase also, right? So now, so imagine this pump field entering the cavity. Because of the nonlinear refractive index, it undergoes self-phase modulation, right? So we saw that an intense field can induce a phase shift on itself proportional to its intensity, right? That's the self-phase modulation. So we'll have a phase shift due to self-phase modulation, right? So so this will be gamma PL, right? So recall the nonlinear phase shift. The self-phase modulation phase shift was gamma PL, right? So gamma is this effective nonlinearity, omega n2 over c times this effective mode area in the waveguide, right? So yeah, depends on n2, which depends on chi3, and then p the power pc is the power of the pump in the cavity, right? Which is enhanced by a factor of the finesse from the power launched in the waveguide. And then, yeah, like this.
Sir, N2 is what?
Sorry?
N2, sir, N2.
Yeah, this is the nonlinear refractive index, right? Remember, this was proportional to chi3. So remember this, there was a delta n which is equal to n2i. So go back to our, yeah, discussion on self-phase. There's that n2. The nonlinear index coefficient. Right? So you can see there's an extra phase shift here, which means that the resonance frequency that we've calculated just from this, it will be slightly shifted because of this extra phase shift, right? So the condition is now this whole thing is a multiple of 2 pi, right? So this is for the pump. So for the pump mode, right? We can look, similarly you can find a condition for any other mode, right? So let's say we look at this mode. Right, so that will also have, so let's call this index n. So for m plus 1, or in general any other resonance except the one where you pump, will again have the linear and non-linear. And linear, again, you can write it as beta times L. But the non-linear for any mode other than the pump, will it be this same, or will there be a slight difference?
Sir, it will be different, sir. I think.
Yeah, how? You're right, it will be different, but how? This is
It depend on the round trip or something.
Yeah, so we are looking at the round trip phase, so the nonlinear contribution, right? So for the pump mode itself, we had to add a nonlinear phase, which was the self phase modulation because of the pump on itself. Now we are looking at some other mode, which is
There
not
would
at
be
the
some cross-phase modulation also.
Cross-phase
Yeah.
modulation and four-way mixing.
So for any other mode, so any other frequency circulating in the cavity, that will experience cross-phase modulation from the pump, right? And you know that cross-phase modulation has a factor of 2 because of the degeneracy factor, right? So this will be the cross-phase modulation, and this is for any other mode apart from the pump. Right, so the pump acquires an extra phase shift gamma PL, whereas other modes acquire extra phase shift 2 gamma P. Of course, we can also consider self phase modulation for these modes, but since we are only pumping at the pump mode, right? Basically, most or all of the intensity is only at the pump frequency, right? So there is no intensity at this field to cause self phase modulation on its own, right? So that's why we don't have a self phase modulation. Or similarly, we don't have cross phase modulation down here from other resonances because there is no power in the other resonances. Okay. So now, if you look at the resonance condition, right? So what was the resonance condition? We just equate this to be a multiple. So for the mth resonance, it's m times 2 pi. Right? So, and again, beta, you can write it as omega over c n effective at omega n. Right? And so from this equation, we can solve for what is the mth resonant frequency omega n. Right? So in the last class, what we did was we just had this term. We didn't have this term at all. So we just saw that mth resonance frequency was n times some c over n effective, something like that, right? But now, mth resonance frequency is so n times the c over n effective L, which is what we had last time. But there's another term minus this 2 gamma p c over n. Okay, so basically there is a shift to lower frequencies. This is a negative, right? So the mth resonance frequency is slightly smaller than what we had got without the nonlinear phase. Right? So which means what? This resonance frequency shifts a little bit towards the lower frequency, right? And this shift you can see is proportional to the pump power, right? So including the nonlinear phase shift, this resonance shifts slightly lower, right? So this linear case where we ignore the nonlinear phase shift, or we say that the power circulating in the cavity is small such that this term is negligible. So this is called the bare or sometimes the cold cavity resonance. Right? And then once we include the nonlinear phase shift due to pumping with a large amount of power, right? Then this shifted is called the hot cavity or shifted resonance. Okay, so these are the resonances in the absence of the pump, right? Or when the pump intensity is very small. But once we pump with an intensity high enough, then this resonance actually shifts downward, right? And you can see the other resonances. So any other resonance, so some omega n which is not equal to m, not n, let me call it k. So that will shift by twice this value. Okay, because the nonlinear phase shift is twice due to the cross phase modulation. So the other resonances will shift by twice the amount. So these resonances will shift by a bigger amount. Right. So if this shift, if you call it x, then these shifts are 2x. Okay. So basically the point is once we have this pump power circulating in the cavity, then the position of the resonances have changed slightly. Okay. And now if you look at this carefully, we can see that this can actually help us to get equal spacing, right? And then satisfy that energy conservation. So let's try to look at that in a bit more detail, how that happens. Okay, so first thing we can imagine a case where maybe let me get more space to make it more clear. Erase this too. So first thing we can consider is a cavity with equally spaced resonances or zero GVD, right? So let's mark resonances here. Hopefully they all look equally spaced. Okay, so let's call this middle mode as the one where we are pumping. So let's call it the 0th mode. So let's say some j equal to 0. So this will be j equal to 1. Okay, so this first case is for 0 GVD, right? So 0 GVD and so the bare cavity resonance. Right, so they're all equally spaced. Or in other words, I can write the mth resonance frequency. So omega m we could write as some omega naught plus d1j, or omega p plus, right, where d1 is some constant. So the mth resonance frequency just goes linearly with the jth resonance frequency goes linearly with the mode number, right? So now let's consider a case where we have anomalous dispersion in the cavity. Okay, so what happens? You remember we have an extra term here, right? So because of the GVD, we have another term here which goes as j square. So the resonances are not equally spaced now. So the resonances to the higher side shift towards higher frequencies a little bit, right? So this one goes here, and they're going as j square, right? So this one will shift a bit more, right? So if this one shifts, let's say x, then this one will shift 4x because it goes as j square, right? So 1 this will be 2 square. So this one will shift even more. This one will shift like 9x. Okay, so now you can see that the FSR is increasing with frequency, right? And on the lower side, so it again goes as j square. So even the -1 will shift upward a little bit. So this will again shift up by amount x, just like this. This one will also shift up by 4x now, like this one. Again, this one will be 9x. Right. So now you can clearly see that the FSR is small here, big here. So the FSR is increasing. Right. So this is anomalous dispersion, bare cavity. Right, without the nonlinear phase. So now, of course, here, so we are pumping here. So of course, we can't get signal and either on any of these any opposite resonances because they are not equally spaced from the pump. But now, when we consider this nonlinear phase shift, or we go from the bare cavity or the cold cavity to the hot cavity or the pump cavity, then we know that these resonances now shift due to the nonlinear phase shift. So the pump resonance we saw will shift downwards, right? So let's call this shift y, and this is we saw something like proportional to gamma times the pump power. And the other resonances will shift by twice of y. Right, so all these all the other resonances will shift by twice of this value y. Okay, so now again we have a new spacing. So this is the hot or pumped cavity. So now, depending on the pump power, right, this y could compensate some of or could compensate the shift, let's say for one particular resonance, right? So for example, if you see here, so let's say y was equal to x. Right, so if y was equal to x, so x depends on the dispersion parameter of the cavity, right, which is just the materials and the dimensions of the waveguide making the cavity. Whereas this y depends on the pump power, how much pump power we send in. Right, so as we change the pump power, we can change y. Let's say we have the pump power set to such that this quantity y becomes equal to this quantity x. You can see then what happens. So if the y is equal to x, so 2y is equal to 2x, so this cavity was shifted up x from this equal spacing grid, and then now it shifts 2x down. So that means from the equal spacing grid, it's shifted down by x. Right? So the pump, of course, it's obvious it's shifted down by x from its original place. Now we can see that the next neighboring resonance is also shifted down by x from the equal spacing grid. Now let's look at this resonance, the other resonance. So this was also again shifted up x from the equal spacing grid, and now it shifts back down by twice that amount. So that means from the equal spacing grid, it's again shifted by x. So now if you look at the spacing between these resonances, they are now equal, right? So this spacing was equal, right? So this is some omega FSR, right? These resonances are just these shifted down by x, right? This shifted down by x is this one, this shifted down by x is this one, this shifted down by x is this one. So these now also have equal spacing, right? But you can check any other resonance that won't be equally spaced from the pump. So this one, for example, the spacing from here is different from this one spacing from here. For y equal to x, right? So now we have a set of resonances which are equally spaced from the pump. So I could get signal and idler to oscillate at these frequencies, right? And this satisfies now 2 omega p equal to omega s plus omega I. Okay, so basically at a particular pump power, the nonlinear phase shifts compensate the dispersion in the cavity, and you get equal spacing, which can get oscillation to happen. Okay. Right. So y equal to x. What is that condition here? So see, y is gamma p c by n effective. Right. So we call that shift in the resonance frequency due to the nonlinear phase shift, and x is just this d2 by 2. Right. So if you have this condition, and d2 recall depended on the beta 2 of the cavity that we had last time. Right. So if this condition is satisfied, so if we have pump power such that all these other things are constants, then we get the first modes from the pump to oscillate. Right. But we could also get other modes to oscillate. So for example, so in general, if y was equal to where do you want to write it? So if y was equal to this d2 by 2 some j square for some value of j. So here we have taken j equal to 1. So for the first resonance, this condition is satisfied. So instead of y, I just write gamma p c over n effective. So if this quantity was equal to d2 by 2 times some j square for some other integer j, then that resonance will become equally spaced. Okay. So for example, again, so if this instead of y equal to x, we had y equal to 4x, then you will see that this one will shift too much. Right. So if we had y equal to 4x, then this one shifts here. This one shifts by twice that amount. So this one has shifted a lot. And this one again is shifted too far. Right, so now the first, so this will be 8x. The shift here will be 8x. And now the first resonances from the pump are not equally spaced. But if you look at the second resonance, so now this shift will be 2y, which is 8x. So it will come here. Which is 4x down from the original equal spacing grid. The pump is also 4x down from the original spacing grid. And now you look at this one, sorry, the second one. This one also shifts by 8, so this one is down 4x from the equal spacing grid. So now if you look at these resonances, so if you take this as omega s, this as omega p, and this as omega I, then this spacing is equal, which is the same as this spacing. Right, and that those modes will oscillate. So now, of course, this is at a different pump. Okay, so yeah, so first point is when we consider the nonlinear phase shifts happening in the cavity, they can actually balance this unequal spacing due to the anomalous dispersion, right? And get a condition where a pair of resonances are equally spaced from the pump, and you can get them to oscillate. And which modes oscillate depends on how much pump power you have. Okay, so I hope that's clear. Any doubts? Okay. Right, so that's from the sort of energy conservation of the photons point of view, right? Or getting the resonance to be equally spaced. But so recall, to get the oscillation going, basically we want the gain in the cavity to overcome the loss, right? So something like a laser action where the gain within the cavity overcomes the loss, only then you will get oscillation or bright light coming out at the signal ideal frequencies, right? So there is some threshold condition, right? So you need a minimum pump power to get some signal or idler out. Right? So we can look at that now. Right, so recall basically if I measure the signal or idler power out as a function of my input pump power, then for low pump powers I don't get anything out. Then there is a threshold beyond which I start getting finite power, right? Just like a laser. And so this value is my threshold power. Right, so when does this threshold condition happen? So this is when gain inside the cavity is equal to loss, right? So loss, recall that how is power lost from the cavity, right? So the loss is happening because photons are leaking out from the cavity, either due to scattering or leaking out into the waveguide, right, or from here. And the energy which is decaying from the cavity, recall, we can write it in terms of the cavity lifetime, which could be written in terms of the Q factor. Right? So basically the energy, so if you don't have any input, the energy will decay from the cavity like that, e to the minus t over tau c, where tau c is the cavity lifetime. And tau c, recall, was Q over omega, right? Where omega, so let's say omega m is the, or we just call it omega p, is the pump frequency, which is one of the resonance frequencies. Right? And then gain is basically the gain due to four-way mixing, right? And recall that for phase matched four-way mixing, the gain went exponentially. Like that, where the small g was gamma p. So for perfectly phase matched four-way mixing, the gain went exponentially with the pump out. Okay, and we can just write it in terms of time by just replacing z is equal to c over n times t. Right, so time and position are related just by the speed. So the gain I can write as e to the 2 gamma p times t. Okay, so my loss is going as something e to the minus some constant times t. My gain is going as e to the some constant times t. So when this constant becomes equal to this constant, then my gain can overcome my loss, right? So when does that happen? So threshold happens when this becomes equal to this. So 2 gamma ECC over ineffective is equal to omega p over q. Okay. So let me call this PC threshold. So we get PC threshold, which is the cavity, which is the power inside the cavity at threshold. Can be written like that. Okay. And then I can replace gamma is equal to omega into C times A effective here. Right,
Sorry,
so the omega
is the frequency. Sir, omega is the frequency of the pump.
Yeah, so omega.
So in the gamma factor.
Yeah. So in gamma also you can take omega is equal to omega. I mean, in general, of course, we have the signal and iter also present, and in general they will have a different omega, right? But the frequencies are close enough that yeah, we can usually just use the center frequency, which is the pump. So okay, so if you put gamma equal to that there, then you get EC threshold is just N effective by 2n2 times this A effective by Q. Okay. So you can see that the threshold is inversely proportional to N2, which is the nonlinearity. Right. So the higher the nonlinearity, the lower power you need. So if the nonlinearity is higher, this threshold will occur at a lower power. It's inversely proportional to Q, which was basically the cavity loss rate, right? Which was also basically, if you look at the resonance, it was the center frequency divided by the width of the resonance. So if you have a high Q, that means you have a narrow resonance, right? And basically the photons stay in the cavity for a longer time. So a higher Q also means a lower threshold. And then a smaller A effective also means a smaller threshold, because smaller A effective, a smaller A effective means you're confining the fields to a smaller cross-sectional area, which means for the same power you have, so each photon has higher intensity, right? Because you're confining it. Right. So this is the power inside the cavity, right? But in our control, what is in control is the power we send into the waveguide here, right? So this is the power inside the cavity. How is it related to the power that we send in from here? Right. So that we know is just
That's
related to the
dependent
physics.
coupling.
Yeah. So, but recall last time we derived. So it depends on the finesse, right? So it depends on the detuning where you are in the cavity and the finesse. So it goes as from f over 1 plus f square or nu over delta nu square, right? This Lorentzian line shape. And at the center, the enhancement is by a factor of finesse. Right? So all these coupling coefficients are all factored into the finesse, right? So recall that finesse was related to the transmission and reflection coefficient here, right? Which is basically your coupling constant of the waveguide. Yeah. So if we are right on resonance with the pump, then we know that the cavity power inside the cavity is the factor of finesse, or f over pi, times the power sent in from the waveguide. So this P in. You see, so if you are right on resonance, then the power in the cavity is enhanced by a factor of finesse compared to the power. So how much power do we need here is then a factor of this lower than the cavity power. So just rewrite this a little bit. So finesse also we know that it's related to Q, right? So basically we want the final answer just in terms of Q and some other constants. So we convert this finesse also into Q. So recall the relation between Q and finesse was this mode. Sorry?
No, I was saying they are directly related to each other.
Yeah, so Q is related to just finesse by the mode number, right? We saw that last time. And we know this resonance condition 2m pi is beta m LR, right? And then beta m we write as 2 pi by lambda, or at the pump wavelength, times n effective. That's the definition of beta, times LR, right? So basically we can write m as LR over lambda by n effective. Right? Which is what, which I guess we know already, that the mode number is the number of wavelengths. Right? So lambda p is the free space wavelength. The wavelength in the medium is lambda p over n. Right? And how many such wavelengths fit in the cavity length LR? That's the mode number. Okay? LR by lambda over n is n. So I can use this for m here. So I can write Q is equal to n effective LR over lambda p times finesse. Or other way, I can write finesse is equal to Q lambda p over n effective LR, and then put this for the finesse here. So I can write PC is equal to P in, right? So now I have a relation between the power in the cavity and the power sent in to the waveguide. So I can write this now, PC in terms of P in. So PC I write as that. So Q lambda P so P in threshold. Right, so just take terms on the other side. So we get the threshold input power okay. So we get Q square. One Q comes from here, one Q was there already. So we get Q square in the denominator. And then we get this product of A effective times LR, the length of the cavity. And A effective times, so A effective is the cross-sectional mode area. And LR is the length. So this is volume, this is mode volume, right? So that's the mode volume in the cavity. I can write as V effective. Okay, so finally I get an expression which is proportional to the cavity mode volume, right? Basically the volume of the optical mode in the cavity here, which means if I have a smaller cavity, then my threshold power is smaller. If I have a large cavity, then I require more power. And it's inversely proportional to Q square, which first of all is showing it's a nonlinear process, right? So linear processes typically will scale linearly with Q. This is scaling Q square, which means, of course, the nonlinear process. So a high Q cavity or a good cavity with low losses helps you a lot, right? Because it goes as Q square. And then other things are the constants. And N2 is again the nonlinearity. So if, that also is coming in the denominator. So you need a large nonlinearity helps. And other things are constants. Okay, so basically you need to do this efficiently. You need very good quality cavities which are very small, right? Then you can do this efficiently. Right, so basically that's the value of this P threshold. As I increase my P in, so I tune my laser to one of the resonance frequencies and keep increasing the power. When the power reaches this value, then suddenly I get two new frequencies coming out, signal diameter. And then if I further increase, I can increase the power in these modes coming out. So which frequencies will come out exactly? Again, is given by that condition that we just discussed, right? So which modes will become equally spaced at this power will be the ones to oscillate. So they could be the nearest ones, or they could be further away ones, depending on where the threshold power is. Okay. So which mode will oscillate first? So again, the condition was, so the jth mode from the pump will oscillate if this j square d2 by 2 is equal to gamma p c c over n effective. But so we know that so this gamma p c over n effective is just omega over 2q. That comes from this gain loss balance, right? Remember this. That's why we started this derivation. So gain was e to the 2 gamma p c over n effective times t, right? So gain equal to loss happens when 2 gamma p c c over n effective is equal to omega p over q. So when this factor is equal to omega p over 2q is when the resonance or the threshold happens. So I can replace the right hand side by omega p over 2q. So you can see the j that will oscillate, and this omega over 2q is also the line width, right? Delta omega over 2. So we call omega over q is the line width here. So delta omega and the center frequency is omega p. So omega p over delta omega is q. So omega over q is delta omega, the line width. Right. So when I equate this to this, you can see that the j is just given by the line width divided by this dispersion parameter d2, square root of that. Right? So basically the closest integer value to this will be the mode, jth mode from the pump which will oscillate, right? So for example, if the cavity line width is 100 megahertz, and if this D2 value is 10 megahertz, then you can see J will be close to 3, like square root of 10 will be 3 point something. So the closest integer will be 3. So that will be the third mode from the pump. Right? So this is the pump. Then 1, 2, third mode. And similarly here, this is the omega I. The third mode from the pump will be the ones which will oscillate. Right? So there is a threshold power that we need to overcome the loss. And at that power, which resonances become equally spaced are the ones which oscillate, which is given by this. Right? So you can see that if delta omega is small or D2 is large, I mean, if first of all they are the same value, then J is sort of 1, which means the first mode will oscillate. But if D2 is very small compared to delta omega, then J will be large, and some faraway mode will oscillate. Okay? So it's basically the interplay between these, the dispersion and the sort of the loss in the cavity, right? So if you have a cavity with very low loss and high dispersion, then the first mode, the node nearest to the pump, will oscillate. If you have the other case where the losses are pretty high compared to the dispersion, or if the dispersion is very small compared to the loss, then some faraway mode will oscillate. Okay, so depending on the materials and the geometry people have used, people have seen, like, for example, the first mode to oscillate, or like 10 modes away, or yeah, different cases. Right? So yeah, I hope that's clear.
Yes, sir.
Right, so these OPOs were first demonstrated in fiber-based cavities, right? So you used to some length of optical fiber and then wound them up into a ring. And initially, they required pretty large pump powers because the cavities were big, right? And typically, so you had to use pulse lasers to get high peak powers to reach the threshold. But then recently, with sort of advancement in nanofabrication techniques, people started making smaller and smaller cavities, optical cavities, right? And now people routinely make micron scale, very small cavities where you can push this threshold power down into the milliwatts, or sometimes people have even shown like into the microwatts, right? So imagine it's like a laser where the threshold power is microwatts and milliwatts, right? That's really small. And of course, you can engineer the wavelengths at which you operate depending on the materials, dispersion, and geometry, etc. So typical materials people use nowadays are silica. Of course, optical fibers are made out of silica, but people now can make really small cavities like microspheres or these microtoroids or even micro rings using silica, very high quality, right? So the quality factors are 10 to the 6, 10 to the 7, 10 to the 8, that kind of range. And other materials are silicon-based materials like silicon nitride, silicon itself. So I posted a couple of papers on Moodle to give you a sort of idea of the developments in these fields. And recently what people have taken this to is, so you can imagine that so you have this cavity, right? So this cavity has equally spaced, or not exactly equally, but sort of some resonances, right? And then, so at the input you send some power in one of these resonances, right? So my input is a single frequency laser whose frequency is like at one of the resonances. And then depending on the conditions here, you get this OPO action to happen. You get four-way mixing to transfer energy to some other modes. So let's say you get these modes to oscillate, right? So the output, now I have these new frequencies. But now you can imagine that if I really crank up the pump power further, the power in these new generated modes will become sort of sufficient to act as pumps on their own. Okay? So basically, initially we just started with one pump, but then we generated light at the signal and idler frequencies. And if this was strong enough, now if the intensity of the signal idler became strong enough, then they can act as their own pumps. So it's as if we are pumping the cavity at this frequency and this frequency also, right? So they might give oscillation at neighboring resonances, their own neighboring resonances. Okay, then there might be mixing between. So now it's as if we are pumping with the three different frequencies, right? So you could have non-degenerate four-way mixing processes also. So you could have omega p, omega s, and now I'm giving to some other omega 3 and omega 4, right? Which could be somewhere like, so omega p, omega s could give like, I don't know, this is omega 3 and omega 4, right? So you could basically cascade and generate sort of this comb of frequencies, right? So you start filling up all the resonances with light due to nonlinear interactions taking place between all the modes. Okay, so instead of just sort of discrete two modes coming out, if you pump it hard enough and the conditions are right, what you end up getting at the output is many, many modes. All spaced by the cavity resonance, cavity FSR. Okay, and this thing is called a frequency comb. So it's called a frequency comb because it looks like a comb, like it looks like a comb with teeth, which are equally spaced in frequency axis. So it's frequency comb. Right. So these frequency combs were first discovered as in mode lock lasers, so pulsed lasers. Turns out, like if you have a very good pulse laser, right, which means you are getting discrete pulses in time, right? If you take the Fourier transform of this, right, you will see that in the frequency domain it has a bunch of frequencies which are equally spaced, where so the spacing in frequency axis here, delta omega, is related to the repetition rate here, delta t, right? And they're just inversely related. And the total bandwidth here, what we call it, I don't know, omega bandwidth, that is related to this pulse width here, or like the pulse width of each pulse. So let me call it, I don't know, tau t. So this omega bandwidth is inversely related to the pulse width. Right? So if you have very short pulses, then you have very wide frequency spectrum. And then the repetition rate in frequency is related to inversely proportional to the repetition rate in time. Right? So these can be very precise. So you can know the timing and this frequency spacing very, very precisely. So it's like a ruler in frequency space. Okay, so you know exactly what these frequencies are to, I don't know, the 10th or 12th decimal place, and you can use it for very precise metrology applications, like in atomic clocks and other places. And so I think in 2005, I think this frequency combs was awarded the Nobel Prize. Right, but so for a long time, people thought that the only way to make these frequency combs is to have some pulsed laser, very good pulsed laser, which typically required, like a mode lock laser requires like a big setup, like at least tabletop with a lot of equipment, and typically quite expensive, and requires precise, like good management of the environment, temperature, humidity, etc. Right, so these were not very easy or compact things to make. But then, so people discovered that using this nonlinear four-way mixing in a cavity, you can get this same frequency comb output. Okay, starting from a single frequency laser. So all you need is just this small cavity which has some nonlinearity, some Kerr nonlinearity, and most materials have Kerr nonlinearity anyway. or all materials have, but most of the commonly used ones, silicon, silica, etc., all have nonlinearity. So all you need is to make a good cavity, which now people have figured out how to make it very small on a very good quality. So you can have chip scale devices, very small, right? And you just pump it with a single frequency laser and you get out this frequency cone. So which required very expensive, one big table-sized equipment. You can do it in a very small, compact device. So this was also a big sort of revolution in the field. And there's now this field has taken off, and a lot of applications have been found. I've also posted a review on Moodle.
So can we say that this cavity is acting like a modulator then?
Cavity is acting like a modulator.
Because sir, if I'm not wrong, sir, can you just first tell me the signal frequency and the ideal frequency? They both have the same power, which was the power of pump, or it's divided by 2?
No, typically it will be lower than the pump, right? So you won't convert 100% of the pump, right? So remember that expressions we derived for conversion efficiency, for four-way mixing, etc., gain, etc., was sort of in the undepleted pump regime, right? So we are still sort of assuming the pump is very strong. So you get bright light out at the signal and idler, but so the best that people have shown for these OPOs is like maybe 10-20% conversion. But yeah, you don't convert like 100% of the pump.
Okay.
So yeah, you can get like 10-20%. But once you get this cascaded process going, then the total power in this comb can be a big, almost like maybe more than 50% of your pump power is now distributed across this comb.
So my basic question is, how it is different from double sideband modulations? Like if I want to relate it from that.
Yeah, sure. So you start with single frequency laser. You have some electro-optic modulator here. You drive it at some RF frequency, and then you generate sidebands, right?
Sir.
And then if you drive it hard enough, you can generate more sidebands. But so okay, one question is how many sidebands can you generate? Okay, so there is some limit on like the modulation index, right? How much RF power you can drive, which means like how much modulation you can get here. So typically you can get maybe tens of lines here when you drive the modulator to maximum with all kinds of amplifiers here and before. You could even cascade modulators, right? So that's also a field of research on its own, electro-optic based frequency combs. Okay, but the limitations are, first of all, how much bandwidth you can get, like how many lines can you get? Typically limited to maybe tens of lines. So maximum, let's say you can do maybe 50 lines, 100 if you stretch, if you like cascade many modulators, etc., etc. Okay. Second limitation is what is the spacing here? That is your RF drive frequency.
RF depend on RF frequency.
Yeah. So that depends on the microwave sources, that RF frequencies, and the electro-optic modulators, which frequencies they can operate. And typically that's less than 100 gigahertz.
Yes.
So the most expensive, best modulators you can get maybe can go up to about 100 gigahertz. Even that is very difficult. So the standard ones go up to like 40 gigahertz. So the spacing here maximum you can get is that. But here, what is the spacing? Right? So here the spacing is the cavity resonance spacing, which is the FSR, right? And FSR we saw was proportional to the length, inversely proportional to the length of the cavity. So when you make these cavities really small, micron scale, which now people make, the FSR that you can get can be much greater than 100 gigahertz, up to even few terahertz. Okay, so the spacing can be much bigger than what you can get with electro-optic modulators, right? So you can, based on the size of the cavity, you can get your FSR to be much bigger. So that's one thing that you can do here, which you can't do here. The second is that people have shown you can cascade this and make this really wide bandwidth. So you can have this what is called octave spanning. So which means this can span a frequency from some let's say omega to 2 omega. Okay, so it goes from a particular frequency twice its frequency. It's called octave spanning. Okay, and people have shown that with this you can get combs which span octaves, which is almost impossible to do with this electro-optic combs, right? Because the number of lines you can get is not many, and also the spacing is not that big. So the relative bandwidth that you get compared to the center frequency is maybe maximum you can do is like 10% of the center frequency. You can get a bandwidth, but here you can get the bandwidth of the order of the center frequency, right? And turns out if you can do this octave spanning, then you can do what is called self-referencing, and basically it becomes much more precise and for all these timing applications, etc., etc. So this is just, I would say, a different regime. You can get frequency combs operating in a different regime, whereas with electro-optic modulators, you get combs operating in a certain limited regime, which of course have their own applications, right? So for optical telecommunications, etc., sometimes the kind of combs we need, we do with this rather than that. But yeah, just a different regime.
Thank you, sir.
So yeah, typically if you want very wide bandwidths and large spacings, then you go for these Kerr kind of combs. These mode lock lasers can also give you very wide bandwidths, octave spanning. So these are, I don't know if you might have heard titanium sapphire lasers, etc. But with mode lock laser also the repetition rate, so this frequency spacing is typically small. I think maximum you can get is like 10 gigahertz. But with these nonlinear Kerr combs, you can get much higher repetition rates.
Sir, why we want that the spacing between the frequencies are much higher?
Now, it depends on your application, right? For some applications, you want small spacing. For some applications, you want large spacing. So I've posted a sort of review paper on frequency combs on Moodle. It sort of lists different applications, or for some applications, you want small spacing. For some, you want large, yeah. Basically, before these Kerr combs, there was no way of how you can get such large repetition rates, right? Both mode lock lasers and these electro-optic modulators could give you repetition rates maximum of the order of tens of gigahertz, and typically more often hundreds of megahertz or few gigahertz. So there was just no way to do it until these Kerr combs came into the picture. Now you can do hundreds of gigahertz or even terahertz. So of course, those would be for different applications than these. Okay, and it's just a very simple setup also. Like you start with just one single frequency laser, and then the output you can get basically a pulse laser, or in the frequency space this very wide frequency cone. Without any additional, this is just a passive device. Even in this electro-optic combs, you need to drive it with RF, so you need extra RF power, RF amplifiers here, RF sources. But here you just need a passive device. So you're just transferring all your input laser energy into these modes.